Hi, my name is Zhou from the Ohio State University. I will be presenting our work, Differentially Private Worst Group Risk Minimization. This is a joint work with Professor Raef Bassily. The problem we study in this work is worst group risk minimization. Given P distributions D1 until dp, the objective is to minimize the maximal population risk across all distributions. This can be equivalently written as the maximal linear combination of the population risks. When each distribution is observed by datasets, we can similarly define the worst group empirical risk minimization. Throughout this work, we consider convex, Lipschitz, and bounded loss, and we assume each group distribution can be accessed via a sample oracle. Worst group risk minimization is a fundamental problem in plenty of applications, such as robust learning, learning with fairness, and agnostic faculty learning, and many others. Differential privacy is a widely adopted mathematical framework that enables designing machine learning algorithms with rigorous privacy guarantees. At a high level, an algorithm A is epsilon delta dp if for any pair of datasets S and S prime differing in one data point, the output of A on S has similar distribution to the output of A on S prime. In this work, we study the worst group risk minimization problem on the epsilon delta dp. In particular, we study two important versions of this problem, the worst group population risk minimization and the worst group empirical risk minimization. In each problem, the goal is to privately find a model with small excess worst group risk. Let K be the total number of samples from all groups, and P be the number of groups, and D is the problem dimension. We give two algorithms for DP worst group population risk minimization, minimax fixed ERM and the approach based on DP online convex optimization. In these expressions, the red part is the non-price optimal rate and the blue part is the price cost. We can also show that this rate, the rate of the minimax fixed ERM is optimal in the offline setting where each distribution is observed by a dataset whose size is fixed beforehand. For DP worst group ERM, we give an algorithm with optimal rate. We first introduce minimax fixed ERM algorithm. We construct a regularized ERM objective FW lambda, and we give a stability result showing that the set point of FW lambda achieves a dimension-independent access risk written in this blue box. Now we give an overview of the algorithm. It's adopted from the fixed ERM framework originally designed for the minimization problem. The algorithm involves solving a sequence of regularized minimax objectives. In iteration T, given the previous iterate WT-1 and dataset collection, we find an approximate saddle point of FT W lambda and privatize the primal parameters WT tilde using the Gaussian mechanism. With properly chosen parameters, we can show that the algorithm is epsilon delta dp and attains an excess risk of square root of p over k plus p square of d over k epsilon. As we mentioned earlier, this rate is optimal in the offline setting. Our second algorithm is based on DP online convex optimization. The general idea is to cast the objective into a two-player zero-sum game. The minimization player can be any generic DP-OCL algorithm, and the maximization player is the multi-unbounded algorithm with privatized gradient estimate. By letting the minimization player be the DP-FT-RL, we can show that our algorithm is epsilon delta dp and attains an excess risk written in this orange box. This rate matches the non-private optimal rate when d is on the order of p square. Finally, we study worst group ERM and propose an algorithm based on a private version of the multiplicative group reweighting method. In iteration T, we first sample a mini batch based on the group weight lambda t. and update the model using the noisy SGD algorithm. And then we compute losses for all groups and privatize them using the Laplace mechanism. Finally, we update the group weights using the multiplicative reweighting method with the privatized losses. Our algorithm is epsilon delta dp and attains an excess worst group empirical risk of p squared of d over k epsilon. And this rate is optimal. Thanks.